Signals, spectra, signal processing. Triangular waveform. The objective is to represent the signal as a summation of harmonic components using trigonometric, combined trigonometric, and exponential Fourier series. The process involves calculating these coefficients through integration over the signal's period, often requiring initial determination of the wave's slope and area. Also provides analysis through real-life simulation, MATLAB and MathCAD, which shows its variation among each other. A triangular wave is defined as a continuous, piecewise linear periodic waveform that moves in a straight linear fashion. Unlike smooth, curved sinusoidal waves, triangular waves are characterized by constant slope segments. This waveform is crucial in real-world applications, including pulse width modulation, PWM, in power electronics, audio synthesis for generating smoother control signals and softer tones in synthesizers, signal testing in control systems, and waveform generation in embedded systems. Its predictable shape and harmonic content makes it ideal for testing linear systems. Furthermore, triangular waves offer advantages over square waves, such as smoother transitions, reduced high-frequency harmonics, easier filtering, and simpler generation using analog or digital methods, making them efficient and practical for both analog and digital signal processing tasks. Mathematical representation. Trigonometric waveform. This form represents the signal as a sum of cosine waves. Due to the wave's even symmetry, only cosine terms are present. Combined trigonometric waveform. Also called the single cosine with phase form. This form explicitly includes the phase shift of each harmonic component. Exponential waveform. A periodic triangular wave is defined by its amplitude, A, and period, T. Its shape consists of linearly increasing and decreasing ramps. The DC component, average value, of the wave is A over 2, calculated as the area under the curve over one period. MathCAD representation. Trigonometric waveform. Combined trigonometric waveform. Exponential waveform. Six, transformation of periodic signals. Amplitude reversal. Amplitude reversal, also known as amplitude inversion or sign flipping, is a signal processing operation that flips the polarity of a signal's amplitude around its zero axis. This means that positive peaks become negative and the negative peaks become positive, while the overall waveform remains the same in terms of period and frequency. Amplitude scaling. Amplitude scaling, also known as gain or multiplication, changes the magnitude or height of a periodic signal by multiplying it with a constant factor. This operation affects the signal's intensity or strength without altering its frequency or waveform. Amplitude shifting. Amplitude shifting a periodic signal involves changing the magnitude of the signal's values, effectively making it taller or shorter by adding a constant value to the signal. This operation changes the signal's mean level, but does not affect its shape or frequency.
Time reversal. Time reversal involves reversing the direction of time. This means that for a periodic signal x of t, the time reverse signal is represented as x of negative t. Essentially, the signal is flipped about the vertical axis. Time scaling. Time scaling, also known as time stretching or compression, alters the time axis of a periodic signal. A positive scaling factor b compresses the signal if b greater than 1 and expands it if 0 is less than b is less than 1. This changes the signal's period and frequency. Time shifting. A periodic signal involves moving it forward or backward in time, either delaying or advancing it. This operation is achieved by adding or subtracting a time shift value to the time variable of the signal function. A positive shift moves the signal to the right, delayed, while a negative shift moves it to the left, advanced.
Actual implementation. Conclusion. The triangular waveform is essential in signal processing due to its precise structure and favorable spectral characteristics, making it a critical tool for engineers. As a continuous, piecewise linear, periodic waveform with constant slope segments, its predictable shape is ideal for testing linear systems and generating smooth control signals. It is widely applied in real-world technologies such as pulse width modulation, PWM, audio synthesis, and signal testing in control systems. Compared to other waveforms, the triangular wave offers smoother transitions and reduced high-frequency harmonics, leading to easier filtering and proving it to be both efficient and practical for analog and digital signal processing tasks. Mathematically, its Fourier series confirms these characteristics, showing it possesses only odd harmonics and its amplitude decays rapidly, designating it as a band-limited and smooth waveform. The practical demonstration involving the 6 fundamental signal transformations, time reversal, scaling, shifting, and their amplitude counterparts, is highly relevant because these are essential tools for manipulating and analyzing waveforms in various applications. By moving from theoretical concepts through modeling in virtual circuits, such as Electronics Workbench, to the final confirmation using actual hardware implementation observed on a digital oscilloscope, the demonstration effectively bridges the gap between theory and real-world application. This process strengthens the foundational knowledge necessary for work in electronics and communication systems, illustrating how concepts like using RC circuits for time shifting or operational amplifiers for amplitude scaling